10.6, starting off, theorem 10.14. If two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So if you look at this circle here, we got our circle. We've got chord AB. We've got chord DC. The point of intersection of the two chords is at point E. So if I wanted to solve for any of the unknown lengths of these chords, I would set up the product of the two parts. So notice how chord AB is turned into two parts, with E being somewhere, not that it's in the middle, but somewhere on there. So you have AE's length and you have EB's length. If you were to multiply these two lengths together, it would be equal to the same thing on the other chord. So AE, the length of AE, times the length of EB would be equal to the length of EC times the length of ED.
Hold on a second, please. I'm trying to understand this.
So what's going to happen is we're not going to have congruent parts anymore like we did in the past, which made it really easy. So you could just set things equal to each other. We're not going to be able to just set things equal to each other anymore. We're not going to have congruent arcs or congruent chords. But we can still solve for unknown parts of the chords by using these theorems that we go through. So everybody have that written down? Okay, so first example. We need to solve for RT and SU. So let's focus just on RT first. RT is divided up by point V. We don't know if that's the midpoint or not. Not quite sure. It could be, but we don't know. What?
Will we ever learn how to determine if a line is going through the midpoint?
Well, if we come up with X being 6, then I know that V is the midpoint when we get our answer. But I'm not sure about that right now. All right, so notice RT is broken up into two parts. It's broken up into RV, and it's broken up into VT. I don't know why I wrote that so big. I need space. RV and VT. So what this theorem says is I can take the product of those two parts and equal it to my other chord in the way that that's divvied up. So that has SV and VU. So I can take the product of SV and VU. You do not need to do this every time. I'm just doing this so you have it in your notes. So what is the length of RV? RV is X. VT is 6. SV is 6. VU is 10. Now we have an equation. 6x equals 60, so x has to equal 10. So if x equals 10...
That does not look like it fits there. That does not look like 10.
It's not drawn to scale. Just go with it.
I have a hard time doing stuff with...
What's the length of RT then?
16.
Good.
It's the same.
And then what's the length of SU? 16 also, right? Because it'd be 6 plus 10.
If that's the case, then it would have to be in the midpoint. They both say the same length.
No, it's not.
So anyway, other lengths have to be the same length?
Yeah. There's no way it's the midpoint. All right. Got that?
I still.
All right, let's do the next one. Dominic, stop talking.
To swallow.
Next one's going to be a little bit more challenging because we've got a lot of X's going on here.
Oh,
So let's focus on chord KJ first. What's going to be the product? What am I going to multiply?
KN and NJ.
Right, so it's going to be, do you want me to do the letters again? Don't put this if you don't want to, but I'll put the letters. So it's going to be Kn times Nj is equal to, if we go the other way, it would be Mn times Nl. So now just substitute in those values. Kn is x. Nj is x plus 4. Mn is x plus 2. NL is x plus 1. Oh boy, now I gotta multiply all this stuff out. What do you get when you multiply the left side? Good. X squared plus 4x equals, what do we get over here? FOIL it. X times x is x squared plus 1x plus 2x plus 2, which when you combine your like terms right here, 1x plus 2x would make 3x. What's going to be nice about this problem? What happens to your x squareds? They're going to cancel because you have the same exact thing on either side. So ignoring those gives you the equation 4x equals 3x plus 2. What does x equal? 2. All right, we're not done. We find ML and JK. So plugging in 2 for x for ML, so that's going to become a 2. That's going to become a 2. So up top we have how long? 4 plus 3. So ML's total length is 7. JK has an X, so that's 2 for that one. Plug in 2 for that X, which is 6. So 6 plus 2 makes 8. Okay. All right. So when two chords intersect with each other on the inside, if we're finding angles, we do this. If we're finding lengths of segments, we have to take the products of the two things. So don't confuse the two. They're going to look the same, but here I don't have any degree signs shown anywhere. That's your first hint. If you have degree signs, then we know that I'm dealing with angles or arc degrees. Here I don't have any degree signs. So that means I'm going to have to find the products of them to solve. All right, so what happens if we have a tangent and a secant? So in this diagram, I want you to label the following. We're going to think of this top section here as the external segment. Dominic, I don't want your opinion right now. Okay. Why do you think we call it the external segment? It's on the outside of it. Good. The whole entire thing is the secant segment. So remember, a secant is something that intersects a circle 2 times. And then down on the bottom we have the tangent segment. So why would the tangent segment not have any part of that segment inside the circle? Right, it's only touching at one point. So in the secant segment, you have the external part, you have the internal part. Can you tell the difference between the two? The inside, the outside, pretty much is the way we're thinking about it. Tangents only have an outside. They're not going to have an inside because it only crosses and touches the circle at one spot, so it doesn't go through the circle at all. All right, so we're going to use those thought processes for theorem 10.15, which is when you have 2 secants. So if 2 secant segments share the same endpoint outside of a circle, then the product, and we have got product going on again, of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. All right, here again, I think a picture is worth a million words, or what's the saying, right? So we've got our circle. I've got segment EB, which is a secant segment. I've got segment ED, which is another secant segment. Because I have two secant segments, I have the internal parts and I have the external parts. What theorem 10.5 or 1.5 tells us is that I can take the external part of one of the secant segments, so EA, and I can multiply it by the whole entire secant segment, which would be EB. You don't write it wrong. And I can equal that to the product of the external of the other secant segment times the whole thing. So EC times ED. So outside times the whole is equal to outside times the whole. If you're on the outside. Does that make sense? Before, if we had two chords intersecting inside, you just took the product of each and equaled them together. But now I have an external part, so it's outside times the whole thing is equal to outside times the whole thing. That's what we're going to be using. All right, does everybody have that written? So if we look at this example, I've got two secant segments. So let's focus on this one first. What's the outside part? 3. So we're going to do the external part, which is 3, times, what's the length? I'm writing too big. Oops, come back. What's the length of the whole entire secant segment?
3x.
Not 3x, 3 plus x. Good. Equals, now do the same thing with the other secant segment. What's the external part? 4. You getting this, Phil? Times what's the whole entire length? 6. Now that should be an equation we all can solve. Distribute. 3 times 3 is 9, plus 3x equals 24. Subtract 9 from both sides. 3x is equal to 15. X is equal to 5. All it was asking us for was to solve for x. Okay. So if you have an external part, external times the whole is equal to external times the whole. It's our second theorem. Ready for the third one? Last one brings that tangent back into our lives. So if you have a secant and a tangent, so if a secant and a tangent segment share an endpoint outside a circle, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. So our secant, that's not changing. External times the whole. That stays the same. But our tangent, like we said, does not have an internal part. So isn't the tangent segment the whole entire segment? Right. So if I think about outside times the whole, well, the outside is the whole. So if I were to multiply EA times EA, what do I really get? EA squared, right? Because the external is the whole thing. So that's where this theorem comes from. Because your tangent doesn't have an interior part, and the exterior is the whole entire thing, we could just take the exterior and square it, which is the same thing as taking the exterior times itself.
I
So we're still thinking exterior times the whole is equal to exterior times the whole. It's just in a tangent, your exterior is the whole thing. So it's just kind of like taking exterior times the whole by squaring it. Okay? All right, let's do the last two examples. So let's do the secant one first, because we're used to that. What's that going to look like as a product?
16
Times.
16 plus x equals 24.
Well, it's not going to be equal to 24. It's 24 squared. 'Cause it's really 24 times 24. Think exterior times the whole. Well, the exterior is the whole. So exterior times the whole would be 24 squared. I don't know what 24 squared is off the top of my head. 24 times 24 is 576.
You do math, idiots.
Does anybody know 16 times 16? You guys don't have one? 256? Plus 16x. So then when we solve that out, 16 squared, subtracting that from 576, gets us 320. Divided by 16 gets us x to equal 20. What's the length of AB?
20.
20, good. There you have it. All right, let's do the last one. Last one, what do we have going for us? Yeah, now I gotta think a little bit. So, let's do the secant first. Exterior of the secant is 8. So 8 times the whole, which is 18, is equal to x squared. 8 times 18 is 144. Oh, isn't that nice? Square root it. What's the square root of 144? 12. Why would it not be plus minus 12? Technically in algebra, we would put a plus minus here. Why would TR not be negative 12 units?
Because you can't have a negative.
Perfect. All right.